Welcome back. MEFB213213 manufacturing processes. All right. If you recall, in the last class we spoke about ultrasonic machining. So if you remember, ultrasonic machining was made of a transformer. Transformer generates the electricity and then ignites the transducer. Transducer oscillates at 30 or 25 kilohertz, and when transducer oscillates, what happens? The tool oscillates. And it will stir the liquid, the abrasive solution, which is made out of silicon carbide, aluminum oxide, and boron carbide, right? So basically what happens is the abrasive liquid will rub against the surface of the workpiece, and it will remove material. So is this material that when it's removing or it's machining the material, is it visible? No, it's not, because you're removing micrometer or nanometer size material. It's very minute. It's not visible to the naked eye. That's why we have a main frame to monitor the material removal rate in the X, Y, and Z axis. Yeah. So once it has achieved the value that you want, then you stop the machining process. So because of that very reason, or very purpose, you choose to do ultrasonic machining and not the normal conventional machining. Yeah. So moving on, let's look at the next one, electrical discharge machining. So EDM, or electrical discharge machining, is the process of removing particles from a conductive metal, yeah, by means of an electric discharge in the presence of dielectric. So here the key word here is conductive material. Your material has to be conductive. What do I mean by conductive? It has to be a metal. Only metal conducts electricity. Yeah, any kind of metal can be used, can be machined under EDM. Can you machine ceramic? No. Can you machine glass? No, because it is a non-conductive material. Yeah. So how does this EDM work? Yeah. So EDM consists of a shape tool or an electrode, and the workpiece is connected to a DC power supply placed in a dielectric. What is a dielectric? It's electrically non-conductive fluid. So if you look at this is an electrical discharge machining. This is your workpiece. Okay, this is your workpiece, and you're placing it in kerosene. Okay, and it has to be a conductive sample. Yeah, it has to be a conductive sample. So when you immerse it in kerosene, there has to be a space between the electrode and the workpiece, because when there is space, you can ignite spark, and every time there is a spark produced, every time a spark is discharged, machining take place. Yeah. So it is to remove a layer of material, but it's not to remove a specific shape. If you want to cut out a butterfly shape, can you do it here? No, you cannot. It's just to do very basic machining. Yeah. So if you look back at the description, when the potential difference between the tool and the workpiece is sufficiently high. So when there's a potential difference, and the potential difference between the tool and the workpiece is sufficiently high, it overcomes the dielectric. So here this is your dielectric, here kerosene is your dielectric, and this is your positive and the negative. So when the potential difference between this is your tool and this is your workpiece. Yeah. So potential difference between your tool and your workpiece is sufficiently high, it will start to discharge spark, and every time a spark is discharged, material removal takes place, and material removal is in the micrometer or nanometer range. Okay, so it will be, once when you discharge a spark, it will be able to overcome this dielectric fluid, and machining takes place. Okay, so functions of a dielectric fluid, or here we use, what's the dielectric fluid used in that example earlier? If you've been using kerosene, yeah. So what's the function of this kerosene? To wash away the product of cutting, to wash away the product of cutting, to maintain a uniform resistance to current flow. So when there is a uniform resistance to current flow, meaning that when there is sufficient potential difference, it discharges spark. That means current is conducting, yeah. So when there is a uniform resistance to current flow, there is uniform cutting conditions, and to provide a cooling medium for the tool and the work. Example of dielectrics is oil and kerosene. Okay, so the rate of metal removal depends on the current density and the frequency of sparks. The rate of metal removal depends on the current density, how dense your current is, and the frequency of spark. That means every one spark, one tiny bit of material is removed. So you need to produce lots of sparks to remove lots and lots of material. So the rate increases. The rate of material removal increases with increasing current density and decreasing frequency of sparks. So your tool has to be designed or shaped to the desired contour of your workpiece. How you want your workpiece to be, that's how your tool is going to be shaped. So where do you use this electrical discharge machining? In die cavities, deep drilling of small diameters, turbine blades and carbides. So advantages can be used for any soft or hard conductive material. Disadvantages is limited to conductive materials. Like I told you, you cannot use it for a non-conductive material, and it's a very small metal removal rate, very very minute. Like I told you, removing nanometer, micrometer size, yeah. So it's more of a precision machining rather than large scale machining, yeah, or mega machining. If you're going to remove lots of material, then you might as well use some other processes like metal cutting, or you can use CNC lathe, CNC mill, yeah. But in this case, because you're doing micro machining, meaning you're removing micrometer and nanometer range materials, so you need to make sure that you need to use this particular material machining technique, yeah. So next one, traveling wire EDM. What is traveling wire EDM? It is a variation of EDM. A slowly moving wire travels along a prescribed path, cutting the workpiece. Meaning that, so if you look at the diagram, yeah, this is your wire EDM. You have your wire. Okay, the wire, the same concept. When the potential difference is sufficiently high between the electrode and the workpiece, you will be, this is your wire electrode and this is your workpiece, yeah. So when the potential difference is sufficiently high, it will discharge sparks and it will machine, okay. And you're going to supply the dielectric fluid through a hose, yeah. So what you see here, okay, you actually, it's like taking a scissors and cutting out the shape. So you're doing it with a wire. The wire actually follows the dimension that you have given. So you have a main frame. In the main frame, you already have your path defined, okay, your machining path defined. So what you're going to just instruct your wire to follow that path, okay, to machine out the product, okay, or to machine out the part. So if say you have you want to machine out a butterfly shape, so you have already defined that in your mainframe. The dimension for that butterfly shape has been defined in the mainframe, and when you press the start button, automatically the potential difference will start increasing. When the potential difference is sufficiently high between the tool, which is your tool, your wire, yeah, and your workpiece, then your machining starts. So it will be able to machine out the butterfly shape precisely. It's just like I told you, yeah, wire EDM is like taking a scissors and cutting out the shape exactly, following the lines, the dimension exactly and precisely. So you do not need to do any other sorts of machining or any sorts of material removal after that, because it will cut out the perfect shape for you, yeah. A perfect shape, it's a butterfly shape, it's a heart shape, whatever shape that you want, it'll machine out that perfect shape for you, okay. So that is wire EDM. So difference between the normal EDM is it just does like surface machining. So there has to be a distance between the electrode, okay, and the workpiece, so that when you discharge spark, material removal takes place. Same thing over here, but here you're using a wire instead of in electrode. As an electrode, the electrode comes in the form of wire, and the wire will be able to follow the defined path, so you are able to get the exact shape, like just like taking a scissors and cutting out the shape. Yeah, so that is your wire EDM. Okay, so that's it for now. Thank you very much. See you until I see you in the next lecture. Thank you.